recording here. All right. Well, welcome everyone to our May ISA New Orleans section technical seminar, and I appreciate everyone joining in on short notice. We were a little late on getting our word out, but looks like everyone. We had a pretty good registration for today, even with the short notice. So we really appreciate you taking an hour out of your day to join our session. Don't really have much to say today. We got our this is our May seminar again. We'll probably take a break over the summer. I know we don't have anything lined up for June at the moment, and probably July either. So most likely we'll have a little bit of a summer vacation, and we'll get back to it in the fall or August most likely. So so with that, I'm just going to turn it over to our guest speaker, Mr. Ken Wright from MS Finbo, and let Ken introduce himself and kind of take it from here. We'll just say typical housekeeping. We're using the Zoom meeting platform, so everyone can unmute their line and ask a question along the way. We just ask that you keep your line muted as always. And then also, if you need to, you could type in a question in the chat or the Q&A panel, and we'll be monitoring that as well. So with that, I'll turn it over to Ken.
Hey, well, thanks, Wayne. Appreciate it. Thanks everybody taking the time on a Tuesday midday here. In presentation mode, I cannot see the chat, Wayne. So if you don't mind monitoring that for me, that would be great.
Will do.
A little bit of background on myself. EE from UNO. Wayne and I actually graduated together, and he reminded me we're quickly upon our 30-year anniversary of graduating. Tough words to say. Can't believe it's been 30 years, but I've been in the consulting engineering business for close to 20. Did about 10 years for an oil and gas telecommunications service company back in the 2000s, and have really spent my entire career in and around technology and technology systems. As we joke here in the office, back in the early 90s, I kind of took that fork in the road on something called communications and wireless technology, and I guess thankfully never looked back. It's been a blessing to be in this industry for so long, and I really appreciate the time from everybody today. The topic for this month is, we called it Enterprise Mobility Solutions for Industrial Facilities. Understanding, I think the basis of the audience here today is in the consulting side, or in maybe the oil and gas or chemical manufacturing type side. I've tried to give it a little bit of a slant in that nature. But I think as we go through the presentation today, hopefully you guys can take away some themes and some big picture items. Also offered to Wayne that certainly if there's anything that you see today, please give feedback to Wayne, or I've got my contact information at the end. I'd be glad to do a deeper dive presentation on any one of these topics. We could easily talk for an hour about anything we're about to show today. So with that, if everybody is ready to rock and roll, we'll jump into it. So today's presentation is really meant to be high level. Hold on one second for me. For some reason, the slide's not advancing. There we go. Kind of take you through a high level overview of what I'm calling enterprise and industrial mobility. So I wanted to start today with just a few quick definitions. Enterprise mobility, I think we all are very familiar with the enterprise word and the mobility word. Maybe not so much put together, but it's really the use of mobile devices, which can be computers, tablets, phones, or other specialty devices for business purposes. You then couple that, if you will, to industrial mobility. Well, it then takes you to the next level, right? So industrial mobility is defined as an approach in which team members can access many types of information from plant floors or field locations. The term implies real-time access to data and connected systems, also known as plant mobility or enterprise mobility. So the point of that there is these two words are somewhat used interchangeably. They're very related and they have similar meanings. So if you see things in the industry, publications and articles with these, with these terms, just wanted to make you quickly aware of what they are. You can imagine there's a very, very broad definition here of what these two items are. So thought maybe we would start with just a couple examples. The first one is obviously a plant environment, whether it's oil and gas refining, chemical, agriculture, et cetera. You see lots of things here in this. You've got hardened spaces, You've got very complex environment that is very unfriendly to RF and RF frequencies. You've got images there of digital twins being developed. You've got real-time data coming from the field, and you've got some other graphical illustrations of a plant. All of these types of items need mobility to capture that data to basically either local to your company's servers or in the cloud to basically be able to serve those back up for, I'll call it, consumption of a variety of user bases. So I think that's probably a very typical one. The second image here is obviously a warehouse. More and more warehouses and distribution centers are becoming more and more sophisticated. We've recently, this year, done a very large consulting project for a major retailer, helping them focus on use of technology to improve their operations and obviously their bottom line and their efficiency of operations in these distribution centers. So that's probably a little bit of a non-traditional one. The top picture on the right is a very simple application where you see a cart that's obviously got some stored goods there. In this case, it's casters. But if you notice the iPad on top of it. So the iPad there is probably serving up the orders and the order picking, if you want to think of that way, electronically. And that device obviously moves all throughout the plant floor. So connectivity is extremely important. And then last but not least, we're now seeing more and more in the robotics space. We've seen where companies are doing pilots and proof of concepts for robotics types applications in warehousing and distribution centers. We've seen other robotics to go into maybe confined spaces and hazardous areas, all of which these robotics have to be controlled through some sort of network. So that's a quick couple examples on mobility. The other terms I wanted to kick off today is, what is Industry 4.0 or IIoT? So these are other very, very common names that you'll see in the industry. Industry 4.0 is what some is calling the new or the latest industrial revolution that focuses on connectivity, automation, machine learning, and real-time data. The industrial Internet of Things obviously is a very close play off of that into IoT, but for industrial sectors and related applications, with a strong focus on machine-to-machine communication. What they call big data and machine learning enables industries such as yours to have better efficiency and reliability in their operations, whether it's through control systems, maybe secondary or tertiary access to control data, whether it's maybe communications within the plant, whether it's maybe through smart equipment. All of those types of devices need some layer of connectivity. So how do you serve up what we just talked about here? What form of communications are really required? So in its most simplest sense, if we're talking mobility and mobility applications, there has to be some form of a wireless solution. So kind of with this introduction piece, now I'm gonna dive in for a few minutes into what are some common wireless solutions that are out in the field today, out in the plants, and maybe some of the pros and cons of each, and then a little bit on a new and emerging technology that's really taken hold, I guess, since probably the middle of 2020. So we're going to walk through today public cellular, Wi-Fi, and private LTE is what I'm calling wireless connectivity alternatives. I think each of us probably have seen the first two, and we're going to talk a fair amount about them. Private LTE is kind of the new entrant into this space. It is kind of circa 2020. It started getting some traction, believe it or not, right as COVID hit. Myself and one of my colleagues was actually at a large international chemical plant in February of 20, talking to them about private LTE for some of the reasons we're going to go through here in a few minutes. More to come on that, but for now, just think of private LTE as a cellular network that is really just built for your enterprise. But I figured I'd start with the easy one, kind of public cellular. Obviously, in South Louisiana, you've got the three main carriers, AT&T, T-Mobile, and Verizon. Any form of smartphones, connected devices such as Apple Watches, such as iPads, any of those types of systems work on their networks. So how are they deployed? Public cellular really is, the basis of it really is built around what they call the macro sites and the tower deployments. We see these going up and down I-10. We see these all over the interstate and through our residential communities. This type of network is out there. It was built to serve street level coverage, if you want to think of it that way. And over the years, it's gotten better. That I would guess probably most of us, if we don't live in a rural area, probably get more than adequate penetration into our homes. And our kids, more often than not, probably get reasonable penetration into their schools and other places like that. If any of y'all follow the wireless industry, you'll see and notice there that there's many frequency bands now that the wireless carriers own and control. They started in the 800 megahertz space, then grew it into the 1900 megahertz. They went back and went actually into a lower band of 700 megahertz, then picked up some additional spectrum in 2100. And now, as of recent, if any of y'all have seen any of the news articles about airports and things of that nature, the 3700 megahertz is actually in the C band, as they're calling it. And we know that the major carriers, AT&T and Verizon particularly, are amidst nationwide C-band rollouts right now. So what does all this mean? So to us as the user of our smartphone or our tablet, it's really invisible to us that device could be working on multiple bands at the same time. It's probably going to be using the lower bands for voice and text type communications. And it's going to be using the higher bands, higher frequencies that have larger bandwidth to support more of our data applications because they want us to have a very robust experience. So what are some of the advantages of public cellular? Well, number one, cellular was always built for mobility. Keyword here today, from its genesis, it wanted to make sure we could go down I-10 at 75 miles an hour and not drop a call, right? So that's how it started. So the roots of the 3GPP standards are really in and around mobility and mobility type applications. Then it became voice and data performance as we know it, 4G, 5G. I give you the ... there because, I'll call it Verizon, at least recently, has now started their additional marketing campaigns about ultra wideband 5G. All that really means is another frequency band where you can get higher data rates and higher throughput, which is great, again, if we're sitting in our offices, probably like we are today, and things of that nature. Again, the low band frequencies are probably going to carry voice and text, and they'll penetrate the average building reasonably well. The higher bands are not going to penetrate so well, and we'll talk about that in a minute. And look, the good news is there's a multitude of end user equipment and options out there at what I call manufacturing scale, which obviously lowers the cost for everybody to be able to have these types of devices. So what are some of the disadvantages of public cellular? Well, number one, the network was absolutely designed for outdoor performance, pure and simple. They've never really tried to get what you would call in-building coverage as part of their designs. If in-building actually becomes a requirement, it's going to need a dedicated solution. What that means is that you would need to put in some type of distributed amplifier system where you're actually bringing the signal from outside to in, maybe by virtue of a rooftop antenna, or moreover, the carriers are now moving towards actually putting a small base station at your building, like a small cell site, if you want to think of it that way. They're very compact, they're very scaled now for enterprises, and they just need an internet connection to get out to the world. What a lot of our customers have really told us is the latter two about public cellular. Is number one, a lack of network control. So if you can imagine, if we're trying to run robots, if we're trying to do automated order picking, if we're trying to get telemetry from the field, we need to make sure that that network is up. And if it's not up, we need to make sure it's in scheduled network outage windows and things of that nature. So any kind of maintenance and stuff could be coordinated. Well, the cellular carriers are certainly not going to offer you that level of control of their network. They're going to do things as they need to because they're trying to serve the most customers at the peak demand times, which may not line up well to an industrial application or need. And then I would say lack of consistent performance in dense asset environments, such as units, structures, maybe even warehouses and things of that nature. Again, for the reasons we've mentioned, these signals don't tend to penetrate those buildings very well. So you're going to get inconsistent results at best. But public cellular certainly has a place. Our company has done a lot of consulting and integration work around bringing cellular communications into hazardous type areas, into blast-proof type buildings, and things of that nature, into operator shelters. So there's ways that you can serve cellular in a dense environment. It just comes with some layer of augmentation. All right, Wi-Fi. I think probably almost everybody on this call has used or is using Wi-Fi in some way, shape, or form at your house, right, at your office, and maybe even in some parts of a plant or related facility. Certainly, Wi-Fi was built and has always been envisioned as what we're calling an enterprise solution, meaning it was built for business. Wi-Fi, since its history, and I'll have a little timeline coming up on the next slide, really up until, let's call it last year, the end of last year, has had two main bands, 2.4 gigahertz and 5 gigahertz. Recently, as of last year, the FCC granted some additional spectrum in the 6 gigahertz range, and now you have manufacturers like Cisco and Aruba and Extreme and others that are coming up with a product called 6E, and we'll talk about that in a couple minutes. But just as a reminder, Wi-Fi works on unlicensed spectrum, and it is very simply what we're calling a contention-based technology, meaning that it's queuing, right? It's got protocols and algorithms built within the technology that understands that multiple people are trying to communicate at the same time. In essence, then it builds a queue, and then it lets you through the queue and it sequences everybody through. Why that's important? Well, certainly in certain applications, there can be some latency challenges, and certain applications are not so kind to latency. So I'm gonna let this slide build. It takes a couple seconds here, but really wanted to walk y'all through kind of quickly the genesis of Wi-Fi. And really here, look at the dates, just go back into the late 90s. Hard to believe it's been around since that time, but really look at the data rates. So the numbers at the bottom underneath the frequencies, and you can see how Wi-Fi has really evolved over the years. Again, these rates, I would tell you, are maybe we would consider it theoretical, or maybe we would call it in a perfect lab environment is a way to think about it. And this takes us all the way through the Wi-Fi 6 standard, which was ratified around 2019 and launched. Not 6E quite yet. But if you notice here, we started at a meager 1 to 2 megabits per second back in the late 90s. And then we jumped into the 2000s, getting up to maybe 54 meg. Then as we progressed more, we got into 6.9 megabits per second, or gigabits per second, sorry, 6,900 there. And as you see, approaching, theoreticals of close to 10 in 2019. So Wi-Fi, I think, has a very specific purpose, and it serves us really well in business and enterprise types applications. So what is 6E then? You may have seen this in the press and some of the trade rags. Again, the major manufacturers have their first generation 6E products out now. It's basically Wi-Fi 6 with more bandwidth. And I've got a slide coming up next that's going to clearly illustrate the increase in capacity, and apologize for the leaf blowers outside the window. So this new band does not need to support any legacy devices. So what I mean by that is basically the chipset of a Wi-Fi device, probably more over this year. There are 6E devices that are now out in the market. I think Samsung has an S22 Plus, I believe. I think Apple is coming out with a device, and some computer manufacturers are looking at embedding the chipset. Think of it as another stream. That they're not going to be, these legacy protocols of the 802.11 G, A, N, and AC are not going to be supported by the new spectrum. It also has some changing in its security, that it's now using what they call WPA3 is required, and it drops that support for WEP and WPA2. And this new protocol has some more inherent, I'll call it, feature benefits and efficiencies that the other legacy spectrums did not have. And certainly it is backwards compatible to 2.5 and 4, meaning you're going to have devices that have both, I'll call it both the legacy bands and the 6E in it. So it's not like it's one or the other. If you want to think of it, it's going to be all three, and there'll be some intelligence in the device in and around how it picks, how it gets you the best experience. And again, this is all driving towards getting the the user the highest possible data rate. So a picture's worth 1,000 words. So if you look along the left-hand column here, you see the frequency band, 2.4, 5, and 6 respectively. I would say most people are probably deploying 20 megahertz channels. So if you want to just take a look here for a second at the top tier of each of these, kind of in that reddish color. In the 2.4 gigahertz, there's three clear channels of 20 megahertz, which is obviously very small and very restricting. 5 gigahertz was a huge jump forward. We went from 3 to 25. But then if you look at 6 gigahertz, or the 6E, we're going from 25 to 60, 20 megahertz channels. So a lot more bandwidth, a lot more ability to have more devices on the air and provide a more robust data throughput. And then for a second, I will say, you'll see under the 5 and 6 respectively, you can aggregate channels. The rules, if you will, the standards allow for channel aggregation. So you can actually go from 20 to 40 to 80 to 160 megahertz channels. So the wider the channel, again, the more throughput that you're going to get. But the less user base that you can serve, again, going back to the comment of thinking of queuing or a contention-based type strategy. So Wi-Fi networks, what are the advantages? I would call it's really good for rapid deployment. You've got manufacturing scale now at what I call a reasonable cost for an access point and a controller, whether it's software-based in the cloud or whether it's a hardware appliance. I mean, it's not over the top for enterprise type system. I would say on a loaded network, we've seen anywhere from 50 to 100 megabits per second, and that's on 5 gigahertz, not 6E, of performance. And the key word there is loaded. Obviously, if you're on an unloaded system, you're going to see much, much higher data rates. Broad device adoption of the chipset. So if you're talking to the Samsungs and the Apples, obviously all of that's covered. And then you've got a nice broad set of what I would call industrial devices and industrial manufacturers that are out there, such as the Panasonics with the Toughbooks. If you guys remember the old Toughbooks, those are still around in different forms and in the Toughbook itself. That's an example of an industrial device. And there's probably at least 5 to 10 very, very reputable manufacturers, companies such as Zebra and related, that are building more industrial or ruggedized type devices that support Wi-Fi. And the good news is that your local IT team gets to manage it and control it. So when is it up? When is it down? When are we doing patches? When are we doing software upgrades? When are we doing updates? Things of that nature. So some of the disadvantages, as I mentioned before, it's unlicensed spectrum. So your neighbor next to you in your house or the neighboring plant can decide that they're going to go roll out a site-wide Wi-Fi network. And when they do that, y'all are all using the same frequencies in essence, and you're subject to interference. Wi-Fi, by nature of the queuing, also has the ability to have high latency. And we've seen that. We've done some very rigorous testing in the field on client networks, and we've forced data transmissions and throughputs with certain sequencing, and you can get delays at times over a second. May not sound like a lot, but if you're in robotics controls or automation or you're controlling a forklift, that can obviously be very detrimental to the control of that space. And other high, I'll call it high sensitivity applications. I think a lot of y'all saw the news of the Teslas over the years. Obviously that needs a very low latency type network to do its automatic control. Wi-Fi, again, because it's unlicensed, it's low power. So it's going to have what we call poor propagation characteristics in dense environments. But the latter two are probably most important here. The technology was never really envisioned for mobility and mobility applications, and roaming and handoff issues are going to cause performance problems. So what I mean by that is when you're moving from one AP to another, and let's say if your particular application is even moving at, I don't know, 8 to 10 miles an hour, maybe like a forklift, for example, and you're moving across multiple APs consecutively, or maybe you're making transitions from indoors to outdoors. you're going to likely have roaming and handoff issues, which may cause your session to drop, your session to disconnect. It may cause your device, like your tablet, to have to force a reboot. All of that is obviously lost time and lost efficiency for the operator, and quite honestly causes them a lot of heartache and dissatisfaction. So if you're in that type of mobility type application, again, probably Wi-Fi in all cases may not be the best application for you. So here's the new technology that's been cooking for several years now, but again, it kind of started to make, I'll call it traction, in and around the summer of COVID, summer of 2020. It's a technology called Private LTE. So LTE is an absolute word that y'all have probably seen. Maybe it was 4G LTE back in the day. LTE stands for long-term evolution. That is absolutely a cellular term that the industry uses to talk about cellular technology. So private LTE, if you want to think about it here, is a private LTE or a private cellular network that is built for an enterprise. Such networks are most commonly deployed at a single site, or maybe in a campus environment at a factory or a plant or a warehouse or a distribution center or a facility such as that. Private LTE networks can be deployed in kind of a wide area network, like for maybe a utility or utility monitoring of transmission and other relaying and maybe sensitive critical equipment. And really, at the heart of it, these private LTE networks differ from the public mobile network in that the latter is really designed to support the consumer smartphone market. If you think about it again, private literally is private. And I'll have a simple block diagram coming up in a minute here, where you as the operator get the chance to deploy your equipment, assign your frequencies, put your security and controls in place, and really have the best, I'll call it the best operational environment possible. So private LTE in the US, it operates in something that the FCC has put aside is what they call the CBRS spectrum. It's band 48 and its frequency is from 3.5 to 3.7 gigahertz. So it's close to the C-band that you saw the carriers starting to launch here, but it is separate. Several people asked that question. It is separate. There are incumbents that are protected by the rules. Believe it or not, it's the US government and the military has always long time used CBRS for lots of applications. So the incumbents are protected as the top tier. There's a second tier called priority access, which is basically a service where a different grade of the license was procured at auction, and you get higher priority for your channels. And then the bottom tier is what they call general authorized access. So most of us on this call would probably fall into a GAA. So what does it look like? So on the left of the block diagram there is some type of CBRS device or band 48 capable device that we buy today. Again, it could be a Samsung or an Apple phone. I believe some of the tablets are now coming out with it. But on the industrial space, there's some companies, there's probably about 5 or 6 companies that have built roadmaps around industrial type tablets and other handhelds that are going to have native CBRS support in it today. So basically, let's just think of it as a phone for a second. That phone is going to talk to what we call an LTE base station. In this case, what that means for us is it's basically a transmitter. That transmitter in some form factors looks kind of like an oversized access point. In other cases, it can be a little more beefy, and I've got some pictures coming up as well. But those devices will talk to the base station. The base station will talk to an EPC. It's a fancy word for what they basically call it, a packet core or a core network switch that assigns all the IP addresses and does all the IP control. That can either be in the cloud or that can be on site or on-prem. And then the difference here is that this spectrum actually is managed by a clearinghouse, if you want to think of it. So the system is smart and it's going to go in and check with the SAS, the Spectrum Access System, to make sure that the frequencies we're transmitting, we're not stepping on anybody else, and then vice versa, the frequencies that somebody else maybe in our general vicinity are transmitting are not stepping on us. So there absolutely is a 100% dependency to the outside world and to the internet for this technology to work. So some of the advantages of CBRS, again, being built on cellular technology, it's scalable. It has increased security by virtue of the next bullet, in that it takes a SIM, a physical SIM card needs to go in your device. So most of these devices that are CBRS capable will have the ability to support multiple SIMs on board, or if not, the person would just have to do SIM swapping if you're trying to move in and out of the network, in and out of a public network to a private network with that device. Administrative control of the system is completely in the hands of the enterprise. Again, you've got the private spectrum, as we call it, available for this type of application. And a lot of people think of this as last mile connectivity to a private network. There's been terms over the years called wireless local loop, or local loops, or things of that nature. Basically, you're taking the wired network all the way to a point, and then you're closing that gap to the end through some type of wireless technology. So maybe what are some of the advantages here? Well, number one, based on this technology being built from cellular, it was built for mobility, it was built for handoffs, it's built for velocity. Obviously, our forklift operators and our robots and things of that nature are not going to challenge anywhere the ability of the technology to do handoffs as you transition from zone to zone. It says it's got the network speed and bandwidth of Wi-Fi with increased reliability. It's just to be clear, it's not going to match Wi-Fi point for point on overall throughput, like in a lab environment. So the trade-off here is you're going to be doing really well with mobility and things of that nature, but you're not going to get as much higher data rates. But typically from what we've seen for IIoT and Industry 4.0 applications, there's no issues here. We've done field testing where we've gotten 80 meg coming off these nodes in the field in a real environment, in a real customer environment. So data rates to the end devices have not been an issue. And the big thing here is density. So in a Wi-Fi network, if y'all can imagine, it, again, by virtue of the unlicensed spectrum and being relatively low power, it has a design criteria typically of around neg 60 dBm, neg 60 to neg 65 on a footprint, whereas this being a cellular technology can go as low as neg 90 and still work just fine. So there's some inherent technological challenges that Wi-Fi has compared to private LTE. And it really comes down to the footprint and the density. So if you're an operator, the good news is you can deploy less nodes. That way you have less nodes to maintain, less nodes to license, less nodes to do break fix on. So one of the advantages that the LTE OEMs are purporting is really you can cover the same amount of geographic footprint with a fraction of the density when you compare it to Wi-Fi. So private LTE implementations are, I'll call it, relatively straightforward. As you see there, it literally is a SIM like we're accustomed to in our phones. It's a SIM-based technology that would go into your device. Your network is built, you power it up. That network would connect to the EPC. That network would then connect out to the internet to get to the SaaS. You would have the ability to do your own programming of your end user equipment by virtue of the SIMs. And you're able to control what we call your fleet of devices for that network. So as you can see here, very much akin to what you have in Wi-Fi, you've got complete control of that environment. But we would say you have an enhanced level of security because of the physical nature of the SIM requirement. All right, so for the next section, I want to transition a little bit to use cases. Our team has been talking to a number of industrial customers for probably about 7 months now, or a little longer, about private LTE. We know several of the major refiners in this area and chemical manufacturers are looking into private LTE technology. So what we pulled together were some of the use cases that we're hearing potential application for. The first one was shutdowns and turnarounds, having a dedicated mobile voice and data network for the personnel and staff that are working the turnarounds, that are trying to update status, maybe update project schedules, maybe deal with field issues and things of that nature. Traditionally, it's been done with either a combination of cellular and push-to-talk radio, but there really has not been an enhanced data solution for turnarounds and related type work. So there's been a fair amount of interest in that space. Certainly, of course, always looking for situational awareness and worker safety. Anything that could be improved there is always, positively seen by the customer base. And we've also was at a show back in February of this year in Baton Rouge where robotics were being introduced for like confined spaces and maybe other hazardous areas, of which all of those robotics type applications are going to be reliant upon some type of wireless connectivity back. Some new things that we're seeing to evolve is maybe more of the critical voice and video communications, either through what we call advanced push to talk or push to video, PTV type services, or maybe in your plant or facility, maybe somebody has used the terminology of wearables, kind of a bit synonymous there. Basically, it's access to maybe a subject matter expert. Your man in the field is wearing something where he can push a button, he can establish an audio connection back to an SME, he can establish a video connection, and they can see real time exactly what's going on in the field. Again, but with that mobility aspect, not at a point or a certain location only. Other clients have talked about predictive maintenance using IoT and analytics. Again, pervasive wireless is certainly a theme there. And then last but not least, on that first image I pushed up there on that first slide was digital twins, augmented reality, virtual reality, digital modeling, things of that nature, all need the genesis of information coming from the field, which can take many forms of wireless connectivity. So a little bit more, is kind of a high bandwidth, mobile connectivity for sensors and the field workers. There's been lots of conversations about drones and drone technology being used, and also video surveillance as well. Our use of this technology, we've consulted with a few customers that have extremely hard to reach areas of their property. It's really cost prohibitive to run fiber out to the edge. They've tried Wi-Fi with varying results. They've tried private microwave, which can be kind of bulky. And they're looking for maybe a simpler solution. And this technology can lend itself pretty well to those types of applications. Of course, on the offshore side, drilling and extraction, for all the reasons where, more and more now they're trying to limit personnel offshore and use technology so they don't have to have as many people on the rigs. And then plant automation, digital insights, real-time data coming off of key sensors and things of that nature, with the ability to stay agile as the use cases change. So we're really seeing the digital transformation and automation is really hot topics across these industries. There seems to be lots of pushes into IoT, artificial intelligence and machine learning, and these other types of applications, which all of it relies on some form of both wired or fiber in this case, and wireless communications to deliver. So some of the benefits we say is private wireless can enable energy companies to digitize and automate their operations and also start to build a pathway for the future. Private LTE is really coming to bear with major manufacturers such as Nokia, who has built cellular equipment for decades, and others, some startups such as Cellular, that are really starting to build this and go after this Industry 4.0 space. And there's really just lots and lots of examples of these solutions providing the high bandwidth, low latency, cellular-like comforts that we're very so much accustomed to over the years of mobility and the ability to access large data files on the go, on the move, at any time from anywhere. So I'm going to transition now for the last few minutes we've got here today into some questions that we're being asked and we're starting to ask our customers. And I only throw these up, these next two slides for the audience here to kind of think about it as it relates to your facilities. Maybe these questions have come up, maybe these topics have come up, but if they haven't, I would think they will. We're seeing large pushes from the corporate level down to the sites and to the assets to really start thinking about the evolution of technology in the plants. Part of it is kind of a self-assessment, is that really are your networks reliable and performance-based and flexible enough to support this digitization push and the automation? What's the cost of a bad connection to operations, to safety, to your staff and to your workforce? Again, kind of my hazardous area or confined space type application. You know, how many different services do you have running? Maybe you have Wi-Fi, maybe you've got LoRa WAN, maybe you've got P25 radio, maybe you've got voice over Wi-Fi, maybe you've got cellular, right? So obviously, like anything, these networks have evolved over the years, and it becomes this amalgamation of different networks for different applications. But really, have you fallen back and really looked at a comprehensive strategy? How many access points do you have required for your site? Do you have them pervasive in the field, or are they in the offices only, the admin areas, maybe the engineering trailers and project areas? Are they really doing their job for you out in the open spaces where you need that mobile connectivity? And then really, what is your vision for your site as it relates to mission critical type applications? I would think mission critical applications are going to need some level of mission critical type communications that have prioritization and provide high qualities of service. So a couple more here. Does your current technology support ultra high bandwidth and low latency type communications? Can it support mission critical voice services, maybe a little more robust than just a standard push to talk radio? Does your site have the foundation for its current and future operations, and standards-based technology that gives you flexibility and agility as these new use cases come about? And are you looking or planning deployment or upgrades in the future for any of these use cases of what we've talked about today? If so, I would think one of the three of those flavors of technology probably should be in the realm of consideration at least. So the magic question is, which is the best wireless infrastructure platform for mobility applications? Well, I'd love to tell you there's a silver bullet. There's not. Each of the technologies I presented today have value and really should be evaluated based on the use cases. We find a lot of times our clients and the technology teams have been heavily, I guess, courted or influenced maybe by OEMs. Those OEMs are absolutely going to push the merits of their technology and the feature set of their products. But a lot of times what we see get skipped over is the actual use cases themselves. Really, we like to start at the foundational level when we do these types of projects and really try to get an understanding of a roadmap, get an understanding of the current use cases today and the success or maybe some of the opportunities for improvement that exist with what's actually there today, and then to springboard into the next piece of this, which would be the roadmap and maybe the short-term future endeavors and applications that are going to be rolled out. So a couple slides here to kind of wrap it up. Well, how should we start? Well, again, document the use cases. It is ultra important, I think, to understand the different stakeholders within your organizations, understand their needs, their requirements, both now and maybe in the short term, to get all of that listed together. So that way you can get a comprehensive view of the world of all of the different problems you're trying to solve, or maybe all of the objectives that you're trying to achieve by virtue of a new network rollout. Then you need to talk about your coverage goals. Once you understand your use cases, is it truly pervasive? Is it 100% of your property? Is it 50% of your property? Is it spot locations? Is it interior? Is it exterior? Is it both? Then performance, right? Let's not lose sight of performance. And performance means both speed and latency, right? So what data rates, what bandwidth do we need to be able to support from our end devices back to the core or back to the cloud, however that's going to happen. And what are their sensitivities to latency? What is that? How well will that application perform in a relative high latency environment? And can it stand it? And will the users accept it? Its performance in that way. And then last but not least would be a physical site assets and infrastructure. So the picture here, you see that fancy backpack that's on that gentleman with the hard hat. That is a RF scanner. It scans about 6 RF frequencies simultaneously. And it can actually provide performance data to understand your current environment. That particular picture happens to be a concrete manufacturing plant on the Gulf Coast. So the virtue of that backpack that you see there would be an RF survey. And this particular one, I was able to put up a little slide to show you of an interior space. Basically, the different colors there show different levels of signal in the area as it stands today. So if you were looking at cellular, that obviously would be very appropriate. If you're looking at Wi-Fi, many of you on this call have probably done ECHO, maybe site walks, site surveys. You would have similar type documentation that would come about to truly show you the current state of your network today, and then maybe where there's some areas that could use some more attention. Survey then turns into RF design. Again, we use tools like ECHO, we use tools like IBWave, where we can actually do RF predictive designs based on the environment. Again, this little caption you see here is an indoor application. All the little white lines on there are walls within the interior of the building. We set up the software that the software understands. In this particular case, those are sheetrock walls, standard construction. There's attenuation values built into the program. So it automatically does the scaling for the signal degradation as it goes through those different media. And then we basically build a consistent network across the top that allows you to achieve the signal levels you need for high performance. We would get into equipment selection, detailed engineering and design, estimating, and then typically at this stage, we would recommend some physical aspect of the build, constructability, if you want to think of it that way, be considered. Then we get into the construction, right? So as you can imagine with like a private LTE or a cellular, it's mostly going to be on a rooftop. It's mostly going to be maybe on a tower, a small communications tower. But in the plants, it's a lot of rooftop type applications. We would need to come up with a comprehensive build plan, understanding how the RF environment and equipment would need to be installed and commissioned. Certainly the selection of end user devices has happened and should be ready for programming and deployment. And then we would go back again once this network is on air with like that backpack, and we would go walk that entire environment again now to make sure and see how close our predictive design actually matches the actual design of what we're seeing in the field. And with that, you should have an operational network at that juncture that your users can start to roll out maybe into a proof of concept or maybe through some beta type users, some friendlies. And there's always some optimization that needs to happen after these networks are built to try to maximize performance for all of your end users. So with that, that's the end of the presentation part. Contact information is here, or you can reach out to Wayne. I know he's got all my information if y'all have any questions or follow-ups, but I'd like to open it up for Q&A.
Excellent, Ken. Very good. Yeah, so go ahead and unmute and ask a question or just type it in the chat. It's like Art, you might have unmuted there.
Yeah, that was an excellent presentation. I always thought I was good at it, but you are very good at it. It's very well done.
Thank you.
I have a I understand that the security and whatnot is in there to keep hackers out, whatever. What about malicious interference? Like some guy coming alongside your plant with a 3,700 megahertz transmitter and just messing you up. I mean, what's the resilience of this stuff for what I would just call malicious interference?
That's a great question. So certainly in the Wi-Fi bands, it's not even malicious. It can be unintentional, right? So again, in that case, because of the 2.4 and 5 gigahertz and now the 6 gigahertz being unlicensed, neighboring plants absolutely could stand up right next to each other, the same technology, and you would have 100% interference. I will tell you that the software is smart in its sense that it's trying to learn your environment. It will do its best to steer away from conflicts by itself. But in some cases, if there's something that just can't be overcome, you would need some human intervention. In the case of what you're saying, and I think that's a great way to put it, some kind of malicious technology. Yeah, there's not a lot you can do about that. If somebody intentionally is outside your facility that happens to know your exact frequencies and sets up a transmitter to stand up destructive interference, you would know it right away. That obviously is one of the first things you'd look for. And there is equipment and procedures that you can go, identify and eradicate that interference. But it would take human intervention once the system tried to, I'll call it agile channel plan around that interference. There's likely it's not going to be able to completely clear it.
Yeah, I would expect it would not cause damage. It would just not work. Like you would shut down or something.
Correct.
We have people shining lasers into pilot eyes. So there's all kind of crazy people out there. And I can see where somebody with a little bit of knowledge could, make it a bad day at a plant by just messing up the RF field.
No, that's correct. That certainly is a risk for sure.
Okay, thank you.
Mm-hmm.
So again, for private LTE, that is something that you don't have to work through the typical cellular providers for. That's something you can do on your own, or you have to work through a Verizon or AT&T to get that equipment.
Nope. That is 100% on your own. It is engineered and built for enterprises. So, company or plant XYZ can reach out to any number of OEMs and engage in that direct discussion. So no, that's a great question. The cellular companies have nothing to do with that set aside part of that CBRS spectrum. That is for private use.
This Arthur again on that same time. I'm straining my brain trying to remember the acronym. But in early cellular days, there was a campus-wide system like PCS or something like that. Mm-hmm. It sounds sort of like what the private LTE is, where you just had your own campus-wide cell system.
Yeah, Arthur, don't recall that ever the cellular carriers, I'll call it, I'm gonna use the figurative term, gave away their spectrum for private use. Maybe moreover, correct, PCS is the 1900 megahertz band. And in the early days, they were probably putting up PCS repeaters at customer sites and on campuses because of the higher frequency to try to get the proper penetration to support voice and data applications. So that was likely a use of the cellular frequencies that the carriers own, but they were putting in some type of amplifiers and augmentation to get good penetration indoors.
Okay, I got you.
So in the early days of Sprint, and I'm dating myself here, but there was a company called Primeco. They were 1900 megahertz only. So again, street level, they did fairly well. But when you got into any level of a building, even an office building, those 1900 megahertz signals at times really struggled.
All right.
Come on, this is too easy. Anybody else?
What is WPA3? What makes that special or better than WPA2?
Well, the three, of course, Wayne. Anything with the three has got to be better than a two. It's the next generation of that associated standard. I am not a security expert, so I don't want misspeak, but basically it is now enhanced algorithms, as I understand it from one of the OEMs. It's a more tighter level of security that's over the air. That's actually, if you want to think of it, encrypting that data that's transferring over the air. That's going from the mobile device to the network controller.
What about another one, I guess, for the private LTE versus a Wi-Fi, like as far as distance, we know kind of Wi-Fi has its limitations on distance. How does
Yeah.
LTE compare?
Well, yeah, so that's a great question. Well, LTE is a lot higher power, or has the ability to be a lot higher power, meaning you don't have to, you can always dial the power back based on your application. But I'll give you an example. We're covering about, let's call it 500,000 square feet outdoors for a client. They have an embedded Wi-Fi solution in place today, and they have order of magnitude of about 20 nodes, 20, to support that area. In private LTE, we can support it with 2. Their 20 nodes, because of the low power, have to be distributed on light poles throughout this property. On a LTE example, we're actually on a rooftop with sectorized antennas pushing the energy directly down onto the target coverage areas and coverage zones. So there's a big difference in equipment quantity and scale between private LTE and Wi-Fi. So less to install, less to maintain, less to license, kind of less, as you can imagine. And look, construction becomes a large part of these cost of these types of projects, especially in complex environments. Running conduit, pulling fiber, having cabinets, right? Converting to PoE, everything that you need to do to support access points and Wi-Fi as we know it today. There can be a very fair construction cost. So not only the less density, but I'll call it somewhat of the simplification of the deployment can yield nice cost savings back to the owner as well.
All right, we got a couple minutes left. We'll let everybody else a chance to formulate a question. Ken mentioned in the beginning that can go deeper dive on some of these things, so I think we will have to invite Ken back maybe in the fall, and we'll do a deeper dive on some technologies here. I think it's a good topic. You know, I think we take a lot of these things for granted. We don't realize the amount of engineering effort that's required, you know, in some of these things. And as an automation provider, we're a little guilty of just, you know, saying, hey, you know, hook up these things and off you go. But it's a lot more to it than that, of course.
As we say, there's lots of fiber and lots of copper to support wireless networks. So yes, lots of rooms, lots of power behind the scenes, lots of interconnects, lots of support infrastructure to make that last mile sing in a true mobility way. And yes, Wayne, there's very specific approaches from an engineering perspective that we've used, and lots of best practices that we've developed over the years for these types of projects. Because the goal is the right outcome, right? The ultimate goal is likely IT is almost never the actual end user, right? They have customers within the organization that they need to serve within operations or turnaround or capital projects, whoever. So the goal is to make sure the true end customers are having the best experience. And that's why we put such a strong emphasis on the front end about interviews with the multiple stakeholders, understanding the pain points, and really making sure we've clearly documented the objectives of the projects. That's really imperative for everybody's overall success, in our opinion.
Excellent. All right. Well, it's about the top of the hour. And if there's no other questions, we'll wrap it up. As always, we appreciate everyone joining, members of our ISA community. We appreciate you taking the time and joining us. And once again, a huge thank you to Ken Wright for this presentation. Ken, there was a request that came in privately to me about the ability to share the presentation. I don't know if you can send me that deck or not. Most of it looked like it was not too sensitive, but
Right.
if you can share it, please do.
Okay. Okay.
And yep. And once again, we do not have a topic lined up yet in June or July, but if we do change our minds and get something, just look for your email. We might wait till the last day again to do that. And anyway, but if not, have a great summer, and thanks for joining.
Thanks, guys. Nice talking to everybody today. Appreciate the time.
Yep. Thank
Thank you,
you,
Ken.
Ken. All right.
Bye-bye.